All right, hey guys, so this is the Thanksgiving week lecture. I will start up where we left off. There are some good memes from last year that I left in the slideshow, so enjoy these to kick off your holiday week. So where we left off last time, and give me a second, I'm gonna flip my laptop into tablet mode. Actually, let me check that I'm recording, because that would be pretty awful if I wasn't. Yeah, okay. So where we left off last time was doing calorimetry problems and phase changes. This time we're going to go back to the world of gases, and we're going to talk about that thing that I mentioned just a little bit in lecture, which is that all gases actually have the same molar specific heat, capital CV. Let me bring up on my other computer the slides here. Okay, so just to make sure I got the numbers right. So I mentioned to you that the reason that this equation with the little n and the capital CV, I'll try and write it with these like braces on it just to remind you that capital is different than lowercase. The reason that this is so useful for ideal gases is that the specific heat per mole of pretty much every gas is going to be the same. So for monoatomic gases, capital CV is equal to 3/2 times the gas constant, and I forget what number that comes out to. It's like 12 or 14 or something. And for diatomic gases, CV is equal to 5/2 R. And you might wonder, like, why is this so universal? Why is it that every gas behaves in the same way? And this is actually a property of a thermodynamic theorem called the equipartition theorem. And what the equipartition theorem says, and I'll have to explain the terminology, is that each degree of freedom, so that's what DOF stands for, degree of freedom, an atom or molecule has is equivalent to contributing 1/2 times the gas constant to capital CV. And a degree of freedom roughly means the amount of ways an object can move. So for a point particle, you have 3 due to translation in the XYZ directions. Whereas for a diatomic particle, you have center of mass movement in all 3 directions, but you also have 2 directions of swinging rotation that are possible. So you get 5/2 R. Now, what's really interesting is that for solids, okay, so like crystals, so I'll draw like a square crystal here of 8 atoms. If you look at the specific heat capacity of most solid crystals, you actually get that their specific heat capacity is 6/2 R, which is pretty cool because there are 3 translational degrees of freedom due to just motion, and then there's also some other theorem that says if you're attached to a spring-like potential energy, you gain another 1/2 R. So for solids, you get 2 pairs of 3. We're not going to use this in class, but something that's really interesting that I brought up last year is what's so interesting about this formula? Like, what's so surprising? And you might be thinking R appears. R is the gas constant. The gas constant. This is a solid crystal. Okay. So that is something that is super surprising how it's universal even across solids. And it really is one of the like miracles of thermodynamics. If you study advanced thermo, you'll see why that is. All right, getting back to the normal slide. So just a reminder, there's 2 kinds of specific heat, and then there's volume and molar for each of them. So I'm going to say completely ignore CP. We will use this next lecture, which I'll cover today. but only as a shortcut. Whereas, like I said, this equation, which is always true, this we'll use a lot. Okay, this CP, it's a shortcut for one very specific kind of process, so it's useful to have in your pocket, but we're not going to use it as much. Okay, so main takeaway from this slide, which you'll actually implement in actual problems, are these two values of capital CV for different kinds of gases. Keep in mind that most problems will try and trick you by just mentioning casually, oh, it's oxygen, and you have to know oxygen is diatomic in order to assign, oh, I secretly know its specific heat is 5/2 R. So we will start by hopping into an example. This is actually the last example on this set of slides. So in this example, a monoatomic gas, and then I give you the hint like that's secretly telling you CV, starts at a certain temperature and pressure, blah, 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 and then an isobaric expansion happens. And I ask you a bunch of things about what happens during the isobaric expansion. Okay, so first, you are asked to sketch the process on a PV diagram. Okay, by the way, if you want to attempt this problem yourself right now, you can pause the video, maybe let me go through a part or two and see how you did by yourself, just to see if you can figure it out yourself. If not, feel free to follow along, and you should have practice on the homework. So on a PV diagram, an isobaric expansion, so that occurs at constant pressure, and it goes from a smaller volume to a bigger volume. Okay, so this is what the process looks like. Part 2, find the number of moles of gas. So just as a reminder, like it's often really advantageous to apply the ideal gas law to the beginning and end moments of the process, because very often you're told 3 of the 4 like state variables, P, V, N, and T. So you can often find the last one just to really make sure you know everything about the gas. So you can, it just opens up your flexibility. You can start using temperature, you can start using moles. Once you know everything, you know that you can do whatever you want. So let's apply it to the beginning. So PV equals nRT. Okay, the pressure is 3 E5. The volume is 100 E minus 6. N is our unknown. R is the gas constant, 8.31. And T, it starts at 373 Kelvin. So if I just divide all those numbers out, I will get N equals 0.01 moles. Okay, so I actually know that at each point here, because the number of moles is assumed to be constant. Okay, next question is find the final temperature. And there are 2 ways you can do this, so I'll show you how to do both. Honestly, the ideal gas law way is probably easier because you know N, you don't know T final, but you know P final and V final at this second point, so you can ideal gas law it. But just to get you in the rhythm in case you aren't told as much stuff, Charles' law tends to be faster. So again, this is an an isobaric process, which tells you Charles' law applies. Okay, this is that T final over T initial equals V final over V initial. And you know every number except for 1. You know every number except for T final. So what you end up getting when you plug in T initial, V final, and V initial is that you get 746 Kelvin. Okay, again, if you wanted to, you could just use the ideal gas law now that you know the number of moles at the end. But just a reminder, like Charles' law is derived from the ideal gas law, so it doesn't really matter which one you use. They're sort of the same thing. Okay, 4. The first law, this is where the new stuff will come in because delta E thermal is finally going to get involved. So we'll get to play around with CV. Okay, so we're going to find how much heat was inputted during the process. So just as a reminder, anytime you see this word heat, it's a great idea to write out the first law. Okay, even if you don't exactly know where you're going yet. So there's your first law. I'll let you copy that down just for a sec. Okay, and again, as a reminder, once you have the first law, there's like two general places you're going to want to edit. Obviously, first, if you want, you can try and highlight your unknowns, but first I like to make some replacements. So delta E thermal, as a reminder, you always replace this with N CV delta T. And work in, this is more situation dependent, right? When you have isothermal processes, you have to use the ln thing. If you have an isobaric process, you have to do a multiplication instead. So in this case, we have an isobaric process. So work in is negative P delta V. Okay, and now it's a good time to check what numbers we know. So I'm just going to rewrite this equation with these substitutions made. Again, just as a reminder, this substitution on the left always happens. This substitution on the right for what form work takes is process dependent. If it's isobaric versus isothermal, you need to do different things. Okay, so I'm just going to rewrite the equation now. And I'm going to also replace delta T and delta V with like T final minus T initial, just to be extra clear. So this should be minus. Okay, and now we just check what variables we know versus don't know. So number of moles of gas is known. CV, it looks like we might not know it, but remember, oh, actually in the original problem I didn't have this hint there. We have a monoatomic gas, which universally has capital CV equals 3/2 R. Okay, T final is unknown, so that's our one variable. T initial is known to be 373 Kelvin. Oh, sorry. T final is not unknown. T final is we just found it here. Okay, heat is our unknown. See, I just saved myself from going in a loop, right? Because I identified here's my unknown. And as soon as I got a second one, I was like, okay, I'm a little concerned that I have two unknowns, so it saved me. Okay, the pressure, remember it's the same pressure because it's isobaric, so that's why I don't have P initial or P final. So the pressure is 3E5. Okay, V final is 200 E minus 6, and V initial is 100 E minus 6. So if you plug in all these numbers, what you're going to get is that Qin is plus 76 joules. So heat was inputted into this gas to allow it to expand at constant temperature. I can now be a good comedian and ask if there are any questions. But I'm not a good comedian, so we're going on to adiabatics. Okay, so we are in a new territory now. Adiabatics. Oh, actually, before I get on to adiabatics, I forgot. There's something I wanted to say. Also, we'll cover radiation in this. Something I wanted to talk about is the shortcut formula involving capital CP. Okay. Again, this is a shortcut formula. The true formula that you really, really use super often is this one with capital CV. This is the important one. This is a trick that lets you go super fast to find Q, the heat, not delta E thermal, for an isobaric process. Okay, there are no other uses for this equation. Okay, so the equation is that the heat required during an isobaric process is N Cp delta T, and Cp has universal values. I just want to double check real quick that I have them right. Yeah, okay. It is 5/2 for monoatomic, 5/2 R for monoatomic gases, and 7/2 R for diatomic. Okay, don't confuse. So it's 5 halves for the monoatomic here. Remember that for CV, the diatomics had CV equals 5 halves. For CP, everything gets cranked up by 2 halves. Okay, so these are universal values. And that's your shortcut equation. Again, it only works to find Q, not delta E thermal, during an isobaric process. You have this in your toolbox if you ever have an isobaric process. In fact, the last example we had, you can do it using this formula. Again, it's an isobaric process, and we were asked to find Q, so technically you can do it in one step. Okay, but I will bring up, we just did that other problem. It took us a little longer, but we didn't have to play with this. So if you ever forget about this formula, you can do it using the plain old first law and ideal gas law. This formula is derived from the ideal gas law. I'll give you a super quick derivation. Okay, so I'm going to write out the first law with work moved over to the other side. Okay, now I have an ideal gas, or sorry, first I have an isobaric compression, so work is negative P delta V. Okay, delta E thermal for an ideal gas is NCV delta T. And now the tricky step, again, you do not need to know this. It's just a derivation of this formula. The tricky step is that P delta V, if you hold the number of moles constant, is equal to NR delta T. So, and again, this is from subtracting 2 copies of that ideal gas law, not dividing, at constant pressure and moles. So this is actually plus NR delta T. So if I factor out N delta T from both these terms, I get that Qin is N and then CV plus another factor of R delta T, and then this is CP. Right, so for an ideal monoatomic gas, CV was 3 halves R, and then I add on another R to get 5 halves R for the value of CP. For a diatomic gas, this CV here would have been 5 halves R. I add on another R to get 7 halves R for CP. Okay, again, this is the main takeaway from this formula, a shortcut process to find the heat inputted during an isobaric process. Okay, now we're on to the main meat, which is the concept of an adiabatic process. So I will quickly define it, and then I'll sort of give some comments on it, but this is what I want to come to your forefront of your brain when I mention the word adiabatic. So the definition is a process where heat exchange is 0, or heat input / output is 0. Okay, so Q in or out, depending on your convention, is 0. That's the definition of what is happening during the real gas. Okay, so what that means is the first law will simplify, right? Whenever heat is mentioned, it's probably a good idea to write out the first law. Okay, and in the case of an adiabatic process, Q is 0, so delta E thermal equals work. Okay, and this is basically where you get from the first law. There are some special ways to find work for an adiabatic process. Is a little complicated. I forget what it is at the moment, so I'm going to put it in quotes, and I'll put an X through it beforehand just to remind us that I don't quite remember. It's 1 over a constant minus 1 t to the constant minus 2. It's something weird like that. I forget what it is at the moment. I won't look it up, and I don't think I'll ever ask you about it. But again, work depending on the process, so whether it's isobaric, isochoric, isothermal, or in this case, a new one, adiabatic, you have a different formula for it. Okay, but this is the main idea that Q is 0, so the first law simplifies to this. Okay, but we will not use that formula. What we will use is a special set of equations that are the analog of Boyle's law, so like a before versus after sort of deal. And those are easier, and I will ask you plenty about them. Okay, just some conceptual information. Again, you don't really need to know these except at a very basic intuitive level. So beforehand, for the past couple lectures, what we've been worried about is holding a state variable of the gas constant. So either keeping the temperature unchanged or holding the pressure fixed or not letting the volume change. This is different. Heat is not like a state variable. It doesn't describe how the gas is doing. It's something that you can add in if you want, if that makes sense. I'm going to be pretty vague about it, but again, if you look at a gas and you ask me how much heat exists here, you're not going to have a good answer. Heat's something you put in or out of the system. Whereas if I give you a gas and I ask you, okay, how hot is it? You can measure that. It tells you how the gas is doing right now, what the dog's doing. In contrast, here, pressure, volume, and temperature are all going to change at once. And we're holding a non-state variable constant. So it's kind of like a weird process. It's not really like the other three. Next, and this is something that can confuse people. So actually we'll put a star here just so you don't get confused and accidentally bite on isothermal stuff. Adiabatic and isothermal are different. Okay, heat being 0 and holding temperature constant are very different things. In fact, during isothermal processes, in order to keep the temperature constant, even as you're messing with the gas, a lot of heat is going to flow in and out to keep the temperature constant. So they're actually opposite, despite how similar they might sound at first. Remember, temperature and heat are very different things, and although they're related in some way, it's actually not it's not one-to-one. Having no temperature change and having no heat change are very different things. In reverse, in adiabatic processes, even though the heat exchanged is 0, the temperature is definitely going to change. That's because basically you're trapping all the heat in the system. It can't leave. In this case, the change in temperature of the gas will come from the work squeezing it and the heat having nowhere left to go. Okay, so here I will give you the main equations for adiabatic processes. So there's only really two. Just as a contrast, I will write for normal, or not normal processes. On the right over here, I'll write for isothermal, we normally have Boyle's law, Pi Vi equals P final V final. Okay, that's for an isothermal process. In contrast, for an adiabatic process, we have this similar looking equation, but there's this constant up here, gamma. It's a numerical universal constant. Okay, and gamma has a value of 5/3 for monoatomic and 7/5, absolutely disgusting number, for a diatomic gas. Okay, again, these are universal and they're told to you often indirectly in the problem statement based on whether it's monoatomic or diatomic. Okay, again, it looks very similar to the Boyle's law equation, but there's this extra factor that completely changes it, and that makes sense. Boyle's law is for a different kind of process, an isothermal process. Here we have a different kind of process, different things are being held, different equation. The derivation of this is a little complicated. You can find it online. I'm pretty sure it's not that insane, but it's definitely not worth showing you. Okay, and there's an alternate form of this. Actually, I already wrote the first law on the last slide, so I can cross this out. The alternate form, which might be useful if you're given temperature instead of pressure, is this one. Okay, and this comes from putting the ideal gas law into this equation. So again, they're secretly the same equation, but just with different variables. Okay, and just as a reminder, the ideal gas law does not have this gamma, right? It's still just PV equals nRT, and it's still true at every instant. Okay, at every instant over the course of an adiabatic squeeze or whatever you're doing, the ideal gas law can still be applied. And again, as a reminder, there is a gamma in these upper equations, but there is no gamma here. Okay, it's just a normal ideal gas law. Nothing has changed. The only thing that's changed is like the Boyle's law stuff. Okay, so here's a summary slide, just in case you ever want to like write it down or have it all in one place. So it lists the CV values, the CP values, and gamma for for monoatomic and diatomic gases. Okay, so I will do a quick summary slide. Oops, what is going on? I'm going to skip the example for a second. I'm going to do a quick summary slide, and then we'll do 2 examples, and that'll be it. So a summary slide so far is that adiabatic means Q equals 0, right? That's the definition of adiabatic. An isothermal process, so delta T equals 0, tells us that delta E thermal equals 0. And again, this comes from delta T equals 0 in delta E is NCV delta T. For an isochoric process in the first law, the work input is 0 because volume is held constant. And then the sort of oddball is for an isobaric process, nothing is equal to 0, but the work is at least very simple. It's pressure times delta V. And I don't really know why I wrote this reminder because I've told you about it a bunch. Okay, so we're going to do 2 quick examples on adiabatic processes, and then we'll wrap up. Okay, so here we have the word adiabatic mentioned. Obviously, that's a red flag that you should use one of the adiabatic equations. And we are told to find the final temperature and volume of a gas during an expansion. So as a general rule of thumb, like if you're explicitly asked about the heat, you want to use the first law. So let me actually scroll up and just mention this to you guys. Oh, here. So writing out this first law, it's only really useful, or it's more useful for problems where you were explicitly asked what is delta E thermal, or work. Whereas these special equations, like the PV to the gammas and stuff, they're more useful when you have a before/after question. So this is definitely a before/after question. Sometimes you'll have to use both, but again, this is a before/after question. So our first instinct will be to look at PV to the gamma equals PV to the gamma. And then maybe if we need to later, if we're asked about work or something, we could use the first law. But our first instinct is going to be to use the PV to the gamma equation. Okay, so find the final volume of the gas. So let's see. Actually, let me quickly peek at my... Okay, so we are told how much the pressure changes, and we're asked about the volume. So this is probably a pretty good formula because it involves both the variable that's being changed and the variable that we want to find. So I'm just going to copy down that equation. Okay, we're asked about the final volume. Okay, so this is our like real variable. Okay, we know. Okay, we actually aren't really told like any of these variables. So gamma is a constant, right? Gamma for diatomic oxygen is going to be 7/5 R. And we're going to have to do work on all these other variables because at first glance, we have like 4 unknowns. We secretly only have 1, but we're going to need to mess around with stuff a little bit. So let's ask ourselves some things. All right, P final and P initial. We do know. Oh no. Okay, we do know. We do know P initial. P initial is 2 atmospheres. And P final, so the pressure is halved. The pressure is just 1 atmosphere. I'll also make a quick remark. Even if they didn't tell you the absolute value of the pressure, you could, by being told the ratio P final divided by P initial, you could divide both sides by P initial and have the ratio appear instead. If you got one of those problems, I think you'd be able to figure it out. So what's really left here is we aren't given the initial volume, which looks like a problem. So it's going to be our job to find the initial volume using other methods. And your first knee jerk is probably, oh, I'm actually told a lot of variables about the gas. I'm told N, T, and P. So I can probably find the initial volume using the ideal gas law. Okay, so just applying the normal ideal gas law for the initial state, right? Because I'm after the initial volume. So I know the initial temperature is 150 plus 273 to convert to Kelvin. I know the number of moles is 0.6. And I know the initial pressure is 2 times, let's see, each atmosphere is 101,300. So I will get out that V initial is 0.0104 meters cubed if I plug that in. So I actually do know this number. By the way, if you wanted to just plug in the variables nRT over P into your formula and not do it in 2 steps, that's fine too. Okay, so now I'm going to rewrite this equation with the actual numbers in it. Okay, so I'm actually going to divide both sides by P final. So 2 atmospheres divided by 1 atmosphere will just give me a factor of 2. And again, this is from P initial, and I'm going to move P final over so I don't have to carry around the conversions from atmospheres to pascals. Okay, V initial is 0.01, and I'm raising that to the 7/5 R power. And that will equal V final to this number. Wait, sorry. Hold on. Have I been saying something bad here? Okay, hold on. Yeah, I just said something really on this slide. So gamma does not have an R attached. Gamma has just the number 7/5. Okay, so this is not 7/5 R. This is just 7/5. Okay, so I know this left-hand side, and now I'm going to raise both sides to the 5/7 power. Remember, when you raise an exponent to another exponent, you multiply the exponents, so they'll cancel to 1. And this tells me that V final will equal 0.017 meters cubed. Okay, you're now asked to find the final temperature. And Actually, it's just quickest to use the ideal gas law, right? You now know the final volume, so apply the ideal gas law. And let's see, you know V final, you know pressure final is 1 atmosphere. You know the number of moles, so that will immediately give you T final. If you wanted to, you could use the other version of this equation, right? You could have used T initial, V initial to the gamma minus 1 equals T final, V final to the gamma minus 1. And that would have been okay too. In my opinion, it's just a little bit harder. If you can use the ideal gas law, always better to do it. And actually, you know what? I'm going to save this example for in class. Okay, just as a closing remark, adiabatics can be confusing. And the reason is you just have more equipment in your toolbox, and some of it is the same and some of it's different, right? You have these new equations with gammas, but at the same time, the ideal gas law stays the same, so you can easily forget that you have that available. And at the same time, the first law is like sort of involved, like heat is mentioned in a lot of places. So it can sort of like sometimes throw you off and make you wonder if you need the first law or things like that. So just try and keep in mind that before versus after, you're probably going to use the PV to the gamma equation versus other scenarios where you don't care about the before and after moments specifically. The simplified first law will probably work, but it'll probably be pretty clear. Okay, so have a great Thanksgiving, no matter when you were watching this. I'll try and post the homework relatively soon, but enjoy the holidays, and I'll see you guys back on Monday.